Let's finish off today's lecture with a summary of all the data structures we've seen to date and what they're supposed to do. So at the beginning of the course, we talked a little bit about lists and double-ended queues, and we talked about the trade-off between arrays and linked data structures. More recently, we've been talking about more powerful abstract data types than a list, like a map or a set, or disjoint sets, which is a special purpose one, or now the priority queue, and all the ways we might implement those. So let's summarize really what we're ultimately getting at, and that is the so-called search problem. Given a stream of data, some collection of information, we want to get back information that we care about. Okay? So for example, if a website, say you're running, I don't know, Friendster here, and you post to your personal page the things that that you only want your friends to know about, it's important to serve content only to friends. Now, even before you ever took this class, you could have written a website that does something like that, or some kind of application, but you wouldn't have necessarily been able to do it efficiently. Okay? But now we know how to do it more efficiently. Or another example, given logs for thousands of weather stations, I want to display weather maps for the specified date and time. I want to say that on some particular day, this is what the weather looked like in the West Coast region. Okay? So that is what these data structures fundamentally are all doing for us. Pretty much all of them that we've seen so far. So what are these search data structures? What do they look like? These are the most abstract level. Well, we have lists, maps, sets, priority queues, and this disjoint sets structure. Okay, are these data types. And so they each have, say, a storage operation where we can put information into the structure. So for a list, we can add things to the list. For a map, we can associate keys with values. Sets, we can add things. Priority queues, again, we add them. And with disjoint sets, the way we store information is to connect stuff up. And then for each of these, there's a way we can retrieve information back from them. For a list, we can ask for a specific index. For a map, we can ask for the value corresponding to a key. A set, we can ask, does this exist in the set? A priority queue, we can say, what is the smallest thing you can give me? And a disjoint sets object can tell us whether or not two things are connected. And so what does it mean to retrieve? Well, I mean, as we've just alluded to, in a list, we're getting it by index. In the map and the set, we're basing it on the identity of the key, information about who the key is. For the priority key, we don't really care about who the key is, we just care about its order. And then finally, for disjoint sets, we're retrieving by two integer values, where each represents an item. These are the search data structures we have built, and each of them is useful for a different conceptual task, and now we know, from what we've done so far, how to implement each of these efficiently. Now, we don't necessarily have to implement things exactly as we have in this class. So this right here is a slide we developed in Lecture Live 2 semesters ago, in which we said, okay, for each of our abstract data types, and we didn't actually do stack in class, by the way, but it's basically just a special list, what are some ways we can implement these things? So sets and maps are very closely associated. They're almost the same data type. The only difference is that a map stores key value mappings, and a set stores keys, but there's really not much to it. Because if, for example, we're using a tree to store it, it's just a matter of what you put in the node. Are you storing just the key, or are you storing a key and a value? Yeah. So for each of these, we have our hash table-based implementations. Either separate chaining, which we talked about in class, where we throw things in a bucket, and we have a different chain for each bucket. Linear probing, which we haven't discussed in our class, but I've included it since it was in the extra slides. The other really good implementation, these so-called blue ones are the efficient ones. So the other implementations we might have here are our trees, right? We have our binary search tree, the vanilla-based one, but it had the trouble that it could get spindly. So we also talked about B trees, 2-3 trees, 2-3-4 trees, how they're perfectly balanced. And then briefly we talked a little bit about red-black trees and how these are really B trees in disguise, and they also get perfect balance. So any of these 4 implementations are quite good at doing sets and maps. This one's okay as a stepping stone to understand this. And yes, we could actually use totally different things. As we saw, we could use a resizing array to do a set or a map, or even a linked list. But in both of those cases, we saw that it was slow. With a linked list, you have to go through the whole list. Could we use a heap somehow to use a set or a map? Sure, why not? I mean, a heap is just a tree. It's a special kind of tree where every item is, if it's a min heap, smaller than its children. You could surely search that tree for anything you want with a set or a map. It's just not going to be particularly quick. It's going to be a very awkward data structure. Okay? Just as I guess you can get to work by riding on the back of your dog, having it drag you through the streets. Yes, it is physically possible, but definitely not what it's designed for. Okay? I mean, it depends on your dog. Okay, how about the priority queue? Well, we talked about a couple of implementations. A heap is a really good one. A balanced tree is also fine. The problem with this one was that we didn't support duplicate priorities, but we could get around it. But as far as performance is concerned, both of these would actually be quite fast, just this one would be a little more awkward. We could also do an ordered linked list, or an ordered array, or whatever else, and those would be slow. And I made this one especially bad, even though I guess it's not much worse, but a chaining hash table, as we mentioned way earlier in this lecture, you could technically use a hash table to implement a priority queue. It would be completely terrible at it because the hash table is all about throwing things into essentially random locations, so you're not going to be able to find the smallest, but you could in principle do it. How about lists? Well, that was Project 1A. We saw two different approaches. And for disjoint sets, well, we had these two approaches, which were not very fast, but worked. And then finally, these two approaches, which were a little more intricate, but very fast, effectively taking almost constant time for each of our operations. Okay? Those are the search data structures. And this is the table that when you walk into midterm 2, you really, really should know. You should be able to do this more or less without blinking. That's your goal, right? So the study guides, everything that I've provided as far as resources go, this is something that should be in your brain. And when you're going to job interviews, you should be able to answer not just the easy questions. How do you build a BST out of a map? But also someone might ask you crazy questions like, what would be the runtime? How would you use a heap, right? Because those kind of questions imply that you have a deep understanding, so that as you go into bigger and better problems than just the ones that have already been solved for the last few decades, you'll be able to do them. So I'll mention just briefly this other neat notion, which is that abstraction often happens in layers. So just as our priority queue could be represented as a heap ordered tree, a tree is not an atomic thing in the Java programming language. You need to represent the tree somehow, and we saw 5 approaches in this lecture, all of them valid. Or likewise, our hash tables. Well, each chain in a hash table, what we get when we look inside of a hash table, what does it contain? It's an array of buckets, an array of places you can put stuff. But each bucket is actually a choice. In the bucket, we talked about in class using a linked list. But you could just as easily use an array list, or a resizing array, or even a binary search tree of all the items in a bucket. Those things are possible. Okay? And then I'll mention lastly specialized searching data structures. So in these type of data structures, we saw a little bit of this. Sometimes, and this is when we talked about delegation versus extension versus adaptation, kind of a little bit fancy OOP for our course, but we talked about how given a list, how could we implement a stack, a queue, or a deck? And so various implementations you might use for these data types, well, you might consider a linked list to store a stack, a queue, or a deck. And both the linked list and a resizing array both work, though I will say that a resizing array is just ever so slightly not as good as a linked list because of resizing, but not really a big deal because amortized time, it's still constant for all these operations. Or you might say for a set or a map. In Java, there are actually interfaces for sorted sets and sorted maps, because sometimes you actually want a set that's in order, so you can ask it, you can throw a bunch of stuff into it, and then you can ask for all the items back in order. And so for these, it makes more sense to use a 2-3 tree or a red-black tree or a BST, and less to use a hash table, because again, they don't support order very well. Or, priority queues. Yes, we have min priority queues versus max priority queues, but I'm not showing them here because of the fact that we can just provide a comparator in principle, and you'll see that in lab. Okay. So to wrap up today's lecture, let's talk actually about everything we've done in the class so far. So the course is titled Data Structures. So what is a data structure? Well, it's a particular way of organizing data. You have some kind of questions, maybe about a database of Friendster connections, maybe about weather, maybe about biology, you have some kind of protein structure information, who knows what. You have some problem that you want to solve with a computer. Okay? And so what we've done is we've now covered many of the most fundamental abstract data types, the thing that you can use to reason about problems, to actually solve these things. Having the ability to, for example, instantiate sets and put stuff inside of them makes your life easier. The ability to create a priority queue makes it much easier to reason about how to collect the top M items from a transaction stream. These abstract data types make it easy to reason about programs, which is critically important if you want to be able to build anything big. Now, of course, computers don't know natively how to do something like a priority queue or a map, right? They're just not built to do that. They actually have more rudimentary pieces. So we have to have this whole hierarchy of abstractions where we go from the abstract data type, and then we have some kind of implementations. And so we've now talked about not just what those fundamental abstract data types are, but also how they're implemented and what the trade-offs are between them. We have an understanding of how arrays versus linked data structures kind of play off each other, right? We're not masters at this point, we just learn asymptotics, but this is the foundation you'll need to be able to reason about how you can implement these really convenient abstract data types that make it possible to reason about solving problems. Okay? So we're going to do two more. We'll do two more in this class. Those are going to be the quad tree, which is an implementation of a spatial or geometric tree, and that'll be on Friday. And then we'll talk about the graph the Monday after spring break, and then we'll say more stuff about graphs. But if you look at what we've done, right? If we look at the Wikipedia article data structures, surely the greatest authority there could be, Wikipedia, we can see we've actually done quite a lot of these, right? And there's a lot of beauty here. So I hope you've been able to appreciate just how much we've actually gotten done so far. And we'll call it a day there, and I will see you next time.